Lab 4, Macroscopic View of DC and RC Circuits. In this lab, we are to predict what will occur in different types of circuits, use multimeters to measure current and potential difference, and examine ohmic resistors and capacitors. So some assumptions made are that all wires, resistors, everything in the circuit is ideal. There is no resistance in the wires used. There's no source for charge dissipation besides elements intentionally included, and that batteries are at full charge throughout the lab. Major concepts used: the loop rule, the sum of the voltage differences across circuit elements sums to zero. Charge conservation, the total electric charge in a system never changes. Steady state, the current at a point in the circuit is constant and does not change over time. And Ohm's law, which relates current, voltage, and resistance. The first simulation is shown here. At each ammeter, the current was 0.02 amps. This is the same because the resistor reduces the current across itself, so the value of the current before and after each resistor is the same. When you reverse one of the ammeters, I predict it to be a negative value, but when you do it in the simulator, it's still a positive 0.02 amps. When you replace one of the ammeters with a voltmeter, these values are both 3 volts because the voltmeter has a positive 3 volt input and no current flowing into the output side of the wire because the wire is not connected. This makes sense because the potential difference from the two 1.5 volt batteries drops from 3 volts to 0 volts when there's a break in the connection. Measuring potential difference across the two batteries, there's a negative 3 volt potential difference across the first resistor. That value is 0.96 volts. The second resistor, 2.0 volts. And when all the values are summed together, it sums to 0, which is expected and predicted. The graph of these voltage drops across each battery, the voltage rises, and then when you hit each resistor, it drops again. Lower slope with the lower valued resistor than the higher valued resistor. When using the voltmeter across the 100 ohm resistor, the current still reads 0.02 amps. When the voltmeter is replaced with an ammeter in parallel with the 100 ohm resistor, the current rises to 0.06 amps. When looking at the arrows, the current only flows through the ammeter and not the resistor. This is because the ammeter is the path of least resistance, so the current would rather flow that way. Calculating resistance, this is using Ohm's law. So you can see those values across the 47 and the 100 ohm resistors. Using a 10 ohm bulb, when the bulb is first connected to the battery, as it's charging the capacitor, the bulb's bright and then dims over time, which happens in both cases. With the battery, it took about 5.39 seconds to charge the capacitor, and then to discharge the capacitor, it took about 10.62 seconds. Using a 20 ohm bulb, these values are almost double, even though the phenomena stays the same. So to charge the capacitor, it took 11.26 seconds, and to discharge, 19.42 seconds. This makes sense because double the resistance in the bulb means double the time to charge the capacitor or discharge it. Time-dependent voltage across a discharging capacitor. So measuring the voltage over 20 seconds, plot the data on an ln delta V over delta V naught versus time plot. The slope of my line was negative 0.1657. The value of the constant RC can be calculated from this. This is the time constant of the circuit and represents the time it takes for the voltage difference to drop 1 over E of its initial value. My experimental value of RC is 6.035 seconds. In theory, it should be 6. When you calculate the percent error, it's a 0.583% error, which is within 2% error bound, which causes my results to be valid. Some remaining questions: what if you were doing this lab in real life and used a real ammeter? What's different about a real ammeter, and what would it change about the circuits that you hooked up? So a real ammeter will have an internal resistance, while an ideal one has 0 internal resistance. So the ammeter would have a potential difference across it, like the resistors did, and change different values within the circuit in the lab. What if you're doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? What would happen in real life? In real life, the battery would lose charge as time went on, and the voltage of the system would not always be 3 volts. The capacitor in our experiment reached full charge within about 20 seconds max. This wouldn't likely happen in real life because the battery used would lose charge over time, and the wire used would most likely have a non-zero resistance as well, which would increase the time that it would take the capacitor to reach that full charge.